I'm going to take a short break from partition functions to talk a little bit about spherical polar coordinates, because it'll turn out that these will be important in considering some of the problems that we need to deal with. Now, most of the time we're working in a system of Cartesian coordinates, so we're working with x, y, and z and functions of x, y, and z, so that if we want to, for example, do an integral of some kind over all space, we might set that up where each of the three coordinates, x, y, and z, are running from minus infinity to infinity. We've got our function, and we're doing it over a volume element of dx, dy, dz. And this volume element is important because this basically is our increment for integration. All right, so the way that might look in a drawing, if I were to draw it out, would be something like this. If I have our three axes, x, y, and z, a point up here would be specified by its coordinates, x, y, and z, and its incremental infinitesimal volume element would just be like a little box that's drawn there where the sides of the box are dx, dy, and dz. All right, that's what would define that box. All right, but it turns out there are certain problems in physics and in chemistry that have a symmetry that is symmetric relative to the origin. That is to say, they have a spherical symmetry. And for this reason, we tend to introduce spherical polar coordinates as a better way to describe those systems because it makes the math a little bit easier. However, when we do this, it's not just a matter of taking our function and rewriting it in terms of these new coordinates. These are the three spherical polar coordinates, but we also have to transform this volume element. Now, to do this, let me first introduce what these spherical polar coordinates are. Okay, they can be defined as x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, and z is equal to r cosine theta. All right. Now, when I draw that, and I'm going to draw this very carefully, and maybe a little bit bigger than I did the last time. So here are my three axes, x, y, and z. And I've got some point out here that would be the point x, y, z. But now I want to describe it in terms of these three new coordinates, r, theta, and phi. Well, first, the r coordinate is pretty easy. It's just the distance from the origin out to this point. So that represents r here in our new coordinate system. The angle theta is basically the angle that this segment makes with the z-axis. The angle phi, I would have to take this segment and project it down into the xy plane, and when I do that, I'll end up with a projection down here, and the angle that that projection makes with the x-axis tells me what the angle phi is going to be. Now, the way we typically define these three new coordinates is we say that r can vary between 0 and infinity. We say that theta can vary between 0 and pi, and phi can vary between phi and 2 pi. So in other words, this phi can go all the way around the xy plane in a circle, but theta can only go down to the negative z-axis, and that's as far as it can go. And it turns out if we were allow it to go to 0 to 2 pi, we would be duplicating half of the coordinates that we have, so we eliminate that redundancy by simply limiting it to 0 to pi. Okay. Well, this is the official definition for spherical polar coordinates, but how do we get that volume element? Well, I'll tell you now that there is an official algebraic way that you can do it. It is fairly straightforward, but it does require a lot of algebra. So what I want to do is basically give you a geometric interpretation of what that volume element might be. Now, in order to do this, since I have a couple of angles here, if I have a distance out here, and I want to rotate this about this point over here, the left point, okay, to some new point. Now let's say that angle that I'm rotating by is some incremental angle. I'll just call it d theta for now. And the length of this segment is r. It turns out that the distance here is going to be related to the length I'm out here. So for example, if it was a much shorter distance, down here, it would be a much shorter displacement. If it was closer to out here, it would be closer displacement. But the displacement itself is proportional to the length of this distance between the two original points. So in fact, I can write that length as basically being r d theta. And I'm going to use that same trick over here when I talk about the volume element in spherical polar coordinates. Let's first consider what happens when we make an incremental addition to r. So if I change r to r plus dr, what does that mean? It means I'm going to go out a little bit farther, and this distance that I've added is dr. Now if I were to take this and increase theta slightly, I would be rotating downward, okay, from here through an angle d theta. And when I do that, so I'll draw this out here a little bit, the distance here is r. Basically the length of this segment here is going to be r d theta, just as it was up here. Now the last one that I need to do is what happens when I make an incremental change in phi. So in other words, if I rotate a little bit further along in phi through an angle d phi, what is the length of that? So I need to bring that up here and draw that length so that now I'll have the three dimensions of a new box that's drawn up here, where one length is dr, one is r d theta, and the last length is the length of this incremental change down here that's been projected up here. Well, the length of this, you can do some geometry and convince yourself, I hope, that this is equal to r cosine theta. That's the length of this line, okay, where this is theta. Well, if that length is r cosine theta, then the length of this little segment here is going to be r cosine theta times d phi. So now our three elements of this infinitesimal volume element are going to be dr for the change in r d theta for the change in theta, and r cosine theta d phi for the change in phi. So when I put all of this together, I end up with a volume element that looks like r squared cosine theta dr d theta d phi. So now if I'm doing an integral like this original integral up here, it's going to look more like this in spherical polar coordinates. I'll have one integral that takes me for d phi from 0 to 2 phi. I'll have another integral in theta that goes from 0 to pi, but now the volume element contains theta in it, so I'll have a factor of cosine theta d theta for that part of the integral. And then finally for r, I'll go from 0 to infinity. I have r squared in the volume element, so I'll have r squared. I'll then have my function, whatever that might be, expressed in these coordinates, dr.